I'm going to record this just anyway, whatever, because I know Mike's got some stuff going on. So let me go share. So here's an idea. So again, the layer is fairly narrow. But the funny thing is when you look at this vertical cross section, that's a relatively narrow layer. But if you think of this as poles and equatorial ridge and the Rossby waves, we get the same type of eddy viscosity that's going on within here. I just think it's kind of interesting. So that's one good part. The next paragraph. Allison, would you read that in small scale? Do you have your book?
I'm speaking with my dad right now. Can you give me?
Oh, okay. Go ahead, Nick.
In small scale.
Second paragraph down there.
I thought I was caught up with it.
Last paragraph of 298.
Oh, 298. Okay. In small scale convection, the kinetic energy generated by the rising of buoyant plumes is parted to the vertical component of the motion. The upward buoyancy force disturbs the balance of forces in the vertical equation of motion, introducing vertical acceleration.
Or inducing.
Oh, inducing vertical accelerations. The vertical overturning that occurs in association with large-scale atmospheric motions cannot be viewed as resulting from buoyancy forces because, in the primitive equations, the vertical equation of motion is replaced by the hydrostatic equation, which has no vertical acceleration term. In
So
large scale,
what they're saying there, right? We talked about this before. Because we take the vertical momentum equation, which is Newton's second law, F equals ma, we're talking about accelerations. An acceleration is a time derivative which makes Newton's second law a prognostic equation. Because we replace that, or in other words, we scale it down into hydrostatic, hydrostatic has no vertical acceleration term. Therefore, the hydrostatic is a diagnostic equation, not a prognostic equation. And there's really good balance between those terms. The only term that fails then would be buoyancy. But again, we've talked about this before, saying if the vertical motion and the vertical momentum equation is replaced by the hydrostatic or scaled to the hydrostatic, then we need to find another way to deal with vertical accelerations, and that would be the quasi-geostrophic omega equation is the big one there. So we can talk about changes in motion, in vertical motion, resulting from both vorticity or differential cyclonic vorticity advection and thermal advection. Okay, keep going.
In large-scale motions, kinetic energy is imparted directly to the horizontal wind field. When warm air rises and cold air sinks, the potential energy that is released does work on the horizontal wind field by forcing it to flow across the isobars from higher toward lower pressure. In the equation for the time rate of change of kinetic energy,
Okay.
do I read it out?
No. Just go ahead and look back at figure 722. Okay, so you notice that there is a circulation where we get cross isobaric flow. So basically the time rate of change of kinetic energy, let's take a look at that. We know that the time rate of change of kinetic energy is 1/2, well here I can do it this way. We can go here, we can go Blackboard. Can you see this okay, guys?
Yep.
Okay.
Epic pen.
I just want to make sure we've got Epic pen going on. Hold on, where are you guys? Oh, you're there. All right. So we have the time rate of change of kinetic energy. Well, taking the derivative of this term, what's the first thing we can get rid of?
1
Get
half
rid of
m.
the half. We can also get rid of the mass because we are saying the mass is not changing. So then we have the derivative velocity squared over time, which think about how long ago we started dealing with this stuff, is 2 times the velocity times the change in the velocity over time. Okay? And what they're going to say here is they talk about in the equation of the time rate of change, the cross isobar flow, which is the velocity dotted the geopotential height gradient, right? That's what that is. So if you imagine that I've got a height gradient, which way does the vector point? Which way does that vector point? This one. Actually, do you agree that I could do this? I could use geopotential height. Either way, I'm kind of looking at the same thing. So maybe I have this. Do you agree that this would be warm air to the south and cool air to the north?
I think the derivative should just be v, dv dt. Remember, you pulled the 1 half out?
No, because I'm taking the derivative of v squared.
Oh, okay, I see what you're doing. Okay.
So if you look at the second term in 7.42, that's the equation. So that's why you're going to get these two terms. So you're taking the velocity and...
Well, I got v squared over, okay, v squared over 2.
Okay, so over here, you are going to have a force that points from high to low pressure, or technically from low to high pressure. It's with the gradient, right? Because the vector points uphill. And if the wind is geostrophic, wind, then what's the dot product of those two things?
0.
Right? That would be 0. But what if the velocity is in the direction of ageostrophic? Let's say we deal with the ageostrophic component. Then we actually have a conversion of kinetic energy because we have a non-zero term. So it says over here, flow across the isobars toward lower pressure is prevalent close to the Earth's surface. I'm sorry, you go back. The cross isobar flow is the one and only source term. So it's just the cross isobar flow of the actual velocity. Flow across isobars toward low pressure is prevalent close to the Earth's surface, where the dissipation term, friction, is most intense. Frictional drag is continually acting to reduce the wind speed. Okay, so think about that, right? Causing it to be subgeostrophic. So the Coriolis force is never quite strong enough to balance the PGF. The imbalance drives a cross isobar flow toward lower pressure, which maintains the kinetic energy of the surface. So when air flows toward low pressure, kinetic energy is being created. And that's because of this term. The first term in 7, on the right-hand side of 7.42. And then they talk about integration so that the generation kinetic energy is equal to the potential energy associated with the rising of warm air and sinking of cold air. So that's the thermally direct circulation. But the idea is that it generates, differential in heating generates cross isobaric flow. And the funny thing is, cross isobaric flow causes an increase in the kinetic energy. Isn't that cool? Eventually, it's going to, but what's that going to do? if you go back to the paragraph at the beginning of 299, actually the 7.4.1, it says it flattens the potential temperature surfaces and weakens the existing horizontal temperature gradients. So the flow is to balance the temperature. But in balancing the temperature, you then create flatter isobaric or isentropic surfaces, which means you've got less temperature advection. Because you've got less temperature advection, your vertical motion fields will become weaker. But because of the thermal wind gradient, the thermal wind relationship, you are now saying that you're going to have a smaller pressure gradient as well. So the flow acts to create less of a, let me do this. I hate talking to you when I'm not seeing you. Where is it? Where did you guys go? There you are. Yay. The idea is this. The surfaces become flatter, you get less of a pressure gradient. So the isentropes become flatter, there's less of a pressure gradient, there's less need for the wind. So what do you have to do to isentropic surfaces?
Bigger slope?
You need a bigger slope. And what causes an isentropic surfaces to slope?
Temperature differentials.
Temperature differentials, right? You're heating the Earth differentially. So the fact that the Earth is a sphere continually creates this differential in the isentropes, the heating between the poles and the equator. So as long as you've got any of these gradients in temperature, isentropes keep wanting to do this. The flow then moves to balance it out. And that's what we mean by saying that the Earth is always trying to adjust to get rid of this imbalance. And that's what flow does. The problem is, and we can kind of go a little bit further, is if you look on page 301, top of page 301, top paragraph right side, the global observing systems. Allison, would you mind reading that?
Mm-hmm. The global observing system describes only the resolvable scales of atmospheric variability, and the analysis is subject to measurement errors even at the large scales. The data assimilation scheme is designed to correct for the systematic errors in the observations and to minimize the impact of random errors on the forecast. The errors in the initial conditions for the numerical weather prediction have been continually shrinking in response to a host of incremental improvements in the observing and data assimilation systems. Nevertheless, there will always remain some degree of uncertainty or errors in the initial condition, and due to the nonlinearity of the atmospheric motions, these errors inevitably amplify with time. Beyond some threshold forecast interval, the forecast fields are, on average, no more like the observed fields against which they are verified than two randomly chosen observed fields for the same time of year are like one another. For the extratropical atmosphere, this so-called limit of deterministic predictability is believed to be on the order of 2 weeks.
Okay, so what you're saying is this is Lorentzian, right? This is what we mean by chaos theory. It's all about the initial condition. The further we go into time, these errors in forecast become larger and larger and larger. They amplify. So what we can try to do is make the initial errors smaller and smaller. But there's a limit in reality to how well we can observe the atmosphere, because it is so vast and huge that the errors don't have to be very much. In fact, think about it. We measure temperatures on an ASOS. It's 24.3 degrees, right? We don't have much precision. Well, what if it was 23.42 degrees versus 23.43 degrees? That initial error will eventually blow up into problematic. So you'd have to make it infinitely small errors to get an infinite large forecast. We can't do that. That's why they're saying it's about 2 weeks in determinist forecasting.
Is that what that spaghetti plot is that you show
The
us?
spaghetti plot, basically what it does is it says, all right, let's take a look at what we have. We've created an environment, and this is when we analyze it, or we do a 0-hour forecast. We objectively analyze the atmosphere. I'm going to introduce small changes or small perturbations in different variables. And if the atmosphere is very sensitive to it, those things will become large more quickly. So the more spaghetti plot, it says to you that the atmosphere is becoming highly sensitive to the initial conditions. So if you're going to write anything down about chaos theory, I would say you need to know this sentence for the rest of your life. Chaos theory is about how sensitive a dynamical system is to initial conditions. And all systems are sensitive to them, but to what degree? So we try to come up with a better initialization, that's great. Try to have better physics, that's great. Parameterizations, that's great. But the reality is we're still limited by this. There are just sometimes we get more predictability and other times we get less predictability. So if you finish up this book, it will talk about the increasing the uncertainty in the forecast with increasing forecast interval is illustrated based on the Lorenz attractor described in box 1.1. In the first experiment shown in the left panel, the initial conditions that make up the ensemble lie within a region of the attractor, for which the forecast uncertainty actually declines for a while as the numerical integration proceeds. So we actually are getting more accurate after the initial conditions. But you'll see that butterfly effect, that's what box 7.26 is. And that was back early on in the book. But there's also all sorts of these outliers, and that's why we do some ensemble forecasting is we don't have any skill at certain levels. But sometimes we do have skill. This is where forecasting experience comes in. We're like, hey, this looks fairly reasonable. If you look at HPC and their forecast, you will see a lot of information that they give about, we have a high confidence or a low confidence. And I personally just think they're guessing, but that's just me. Okay, so that's the atmosphere kind of in a large dynamical sense. Now, it wouldn't be my class if I didn't show you this movie, which I realized I didn't show. And that's the only thing we didn't get through. I was really happy with this class. So, waves in fluids, time fixed. Or the audio, maybe I don't want time fixed, I want audio corrected. Yep. So we're gonna watch this movie together and then we'll call it a day. We'll call it a semester. But this is such a great movie, folks. And we'll be stopping and talking about some of these things. Can you hear it okay?
Yeah.
Mm-hmm. Very dramatic.
Waves occur all around us. Most common, perhaps, are gravity waves in water and compressibility waves in air. Because waves in water are easy to observe, we will begin with them. Later, we will see that many of the concepts we have developed with these gravity waves apply equally well to compressibility waves in gases. A surface gravity wave is a region of increased or decreased depth that moves relative to the fluid. A large amplitude wave produces a large change in depth as it goes by. When the change in depth is small compared to both mean depth and wavelength, we call it a small amplitude wave. Even when we cannot see the surface, we can detect the passage of a wave by the change in pressure at a fixed point. We can also detect it by the motion of the fluid particles. These solid particles are very nearly the same density as water and hence move like fluid particles. Note that the motion of the fluid is very limited in comparison.
By the way, we did this in 1119. Those of you who took it, we did tsunamis. We did a lot of this stuff.
With the motion of the wave. Here, the wavelength is comparable to the depth. In these waves, the particles move in circular paths. The diameter of the circles decreases with depth. The particles near the bottom hardly move at all.
So, in other words, if you were sitting there in a wave near the ocean, and you've got the waves going on in a big storm, if you wanted to avoid those waves, you would go deeper. Because the deeper you go, the smaller the amplitude of the oscillations. And remember that a circle is nothing more than a horizontal oscillation. At the same time, you're getting a vertical oscillation. So if you move it vertically, you are going to get, and horizontally, you're going to get vectors that go in circles.
This is the pattern of fluid movement characteristic of waves on the surface of deep water. That is where the wavelength is comparable to or less than the depth.
Wait, say that again.
This is the pattern of fluid movement characteristic of waves on the surface of deep water. That is where the wavelength is comparable to or less than the depth.
The wavelength is less than or comparable, but less than the depth. So if you have a wavelength, lambda, that's going to be less than d, the depth of the water. Okay, a tsunami is a shallow water wave because its wavelength is way longer, like thousands of kilometers compared to the depth. So this is a deep water wave. So wind creates waves. Those are called deep water waves.
Shallow water waves are waves with wavelength long compared to the depth. This is the characteristic pattern of particle motion for shallow water waves. Notice that the horizontal amplitude of the particle motions is nearly the same at all depths.
Does that make sense? So you get, and notice it's the horizontal sloshing back and forth. So when you have a wave, imagine this, you have a wave with a very long wavelength, but it's going to be steep or sloping, even though it's shallow sloping, it's going to be for a long time. And so that creates a gradient that's going to cause the water or the particles to try to move toward this region of lower pressure off to the side. So the horizontal motion is going to be pretty much the same everywhere. Vertical motions are pretty small, so rather than making circles, what are they going to make?
Ellipses?
Very, very shallow ellipses, right? And when you get close to the shore, they're making ellipses, but they're really much more like straight lines. So there's actual mass motion inshore, on land, and offshore. So you get this strong horizontal motion, and that's what's known as a shallow water wave.
We say that such waves are essentially one-dimensional, since the horizontal fluid motion depends only on time and horizontal distance from a reference point. Because they are simpler and yet display most of the important features of wave motion, we would use one-dimensional waves for further study. Not all waves are periodic. We can send a single step wave down the channel. And for our purposes, we may consider either a step wave that increases the depth or a step wave that decreases the depth. Note the movement of the fluid particles as a step wave passes. In the undisturbed water ahead of the wave, the fluid is at rest. After the wave has passed, the fluid is moving in the same direction as the wave at a constant speed.
Okay, so think about this, right? Now you have motion generated that's going to be motion of the particles, that's V. You have a motion of the wave, that's C. So when we talk about V and C in dynamics, C is oftentimes the wave speed, V is the velocity of the individual molecules or the parcels or whatever you want to say.
Each of the wave accelerated the fluid. Watch one particle again. While the wave moves from here to here, the particle moves through a much shorter distance. These particle images were recorded at equal time intervals. So, from the spacing, it is clear that the wave is a region of acceleration. If we let the wave continue out of frame, we see that the particle is no longer accelerating, but moving at a constant speed. Fluid acceleration occurs only during the time the depth is changing. The depth in a given region can only increase if more fluid is moving into it than is moving out, a simple statement of the conservation of matter. And clearly the fluid velocity is higher here than here. Now here's a wave that decreases the depth. More fluid must be flowing out of a given length of the channel than flowing in for the depth to decrease. The particles ahead of the wave are at rest. Those behind it are moving at a constant speed. The decrease in depth is accompanied by an acceleration of the fluid.
So cool.
While the wave moved this far, the particle moved this distance, accelerating in the opposite direction, as our multiple exposure shows. And as the wave moves on out of the frame, we see the particle continuing to move with constant speed.
So in other words, do you remember what it said? When does the particle change its speed?
Ahead of the wave.
Yeah, what's changing? He made quick mention of it. The particles change their speed only when the depth is changing. Okay? So once the depth changes, the particles change their speed. Once the depth becomes constant, then the particles move at a constant speed again. This is kind of important if you think about waves in the atmosphere. Right? As the heights are falling, you are now starting to accelerate the air. That's where you start getting these jet maxes.
What force causes the fluid to accelerate? It is a force arising from differences in pressure.
Pressure gradient force.
Note how the pressure at the bottom of the channel increases as this wave goes by.
So weight of the air above you, weight of the water above you, pressure goes up.
For these shallow water waves, the vertical acceleration of the fluid is small compared to the gravitational acceleration. Thus, the vertical pressure variation is nearly hydrostatic. That is, the pressure is atmospheric at the surface and increases almost linearly with depth. The pressure difference,
now you're talking about the water pressure. So at the top of the water, the only air pressure acting on it is the air pressure from above. That's why it says the atmospheric pressure. Since water is an incompressible fluid, right? Except for temperature. And we're not looking at water that would have any reason to have a different temperature. The change in the pressure is linear. Now, in our atmosphere, would this be a linear change in pressure? Like, does the atmosphere change linearly as we come further down to the atmosphere? No, it's going to change exponentially because the atmosphere compresses. The atmosphere is not an incompressible fluid. Its density changes. And that's the difference between a water wave and an atmospheric wave.
Horizontal direction is nearly the same at all depths, which means that the horizontal acceleration is nearly the same at all depths.
So that little triangle thing is just saying the value of the pressure, because this is deeper water, is over there. But the difference at each height is the same. It's a linear difference. So that's why all the particles accelerate at the same speed. That would not be true of the atmosphere.
As this wave passes, the pressure on a fluid particle increases. For this reason, we may call this type of wave a compression wave. Note that the fluid acceleration is in the direction of wave motion. In this wave, the fluid acceleration is in a direction opposite to the wave motion. This is so because the pressure is higher at the leading edge of the wave than at the trailing edge. As this wave passes, the pressure on a fluid particle decreases. Hence, we may call this type of wave an expansion wave, in contrast to the compression wave. In both cases, the vertical pressure gradient arises because of the gravitational force acting on the fluid. Thus, it is really gravity that causes these waves. Whenever the fluid surface is not horizontal, a horizontal pressure gradient is produced by gravity that accelerates the fluid horizontally. We have viewed the waves in a reference frame at rest with respect to the fluid ahead of the wave. Let us change our frame of reference and move with the advancing wave so that we can watch the shape of the wave.
Right? This would be talking about relative to the wave, kind of in a storm relative sense, so that rather than going backwards, now it's going to go forward, just not as fast. So in a relative sense, right? That's how things have changed.
As it advances, the compression wave appears to steepen, the trailing edge overtaking the leading edge.
So we have a wave that's amplifying. If the gradient, the slope of the wave is the amplitude, we have a much stronger amplitude wave.
The expansion wave, on the other hand, flattens out, the trailing edge falling behind the leading edge. Differences in local fluid velocity and depth within the wave itself alter its configuration as it advances. Where the depth is greater, that portion of the wave travels faster. We can see this variation in wave speed quite easily. Here is a depth of 1 inch, here is a depth of 4 inches, and here one of 9 inches. Small amplitude waves pass this line at the same instant. Obviously, their velocities are different. The wave in the deepest water traveling fastest. In fact, their velocities are in a ratio of 1 to 2 to 3, directly proportional to the square root of the depth. The wave speed is given by the square root of gh, where h is the depth. This fact, that the wave speed relative to the fluid, the local wave speed increases with depth is one reason why an expansion wave tends to spread out as it moves. We can describe the velocity of the leading edge of the expansion wave relative to the fluid as square root of GH1. Similarly, we can describe the velocity of the trailing edge relative to the fluid as square root of GH2. Clearly, the local wave speed at the shallower trailing edge is less than the local wave speed at the deeper leading edge. But there is another factor at work here. The local wave velocity is always stated relative to the local fluid velocity. Now, we have already seen that the fluid at the trailing edge of an expansion wave is moving away from the fluid at the leading edge. So, relative to the leading edge, the slower speed of the trailing edge is rendered even slower by virtue of a local fluid velocity there in the opposite direction.
Because it's backwards.
The fact that the local wave velocity increases with depth also explains why the compression wave tends to steepen. The local wave velocity
Not showing up
is
super
higher
well, but that's
at
okay.
the deeper trailing edge of the wave than at the shallower leading edge.
But
Furthermore, in compression waves, the fluid at the trailing edge is moving toward the leading edge. This local fluid speed adds to the increased local wave speed at the trailing edge, causing the trailing edge to overtake the leading edge even more quickly.
I was told a long time ago by a Canadian meteorologist, he goes, I learned more about the weather because I took fluid dynamics from a physicist, not an atmospheric scientist. And that's because an atmospheric scientist, right, we do this kind of stuff in dynamics, but you don't really understand what's going on until you start seeing it from a physics, because a physics doesn't care about the atmosphere. They're just going here. Here's how waves and fluids work. But now you start looking at this going, so this is how we transform to the atmosphere. I think it's amazing. Now, do you see what's going to happen in this scenario?
This way,
When the wave is a compression wave, what is the slope of the surface going to do?
It's smaller.
No, if it's a compression wave like this one. The slope of that surface gets steeper and steeper, doesn't it?
Right.
Okay, well, what happens eventually if it goes
Goes vertical.
too much? Well, do you understand this? Even if it goes over, do you see that it's gonna the water can't be up here more than the water on the bottom. So the water is going to start to turn over. It's going to what we call a break. There's a break in the wave. So
they
watch
steepen
this.
in slow motion as we follow its leading edge. What happens now? Anyone who has been to the beach
Not even
knows
vertical.
the answer. The wave topples over. Note that the toppled wave moved out of our picture, which
Now, the toppled wave moves out of our picture, which means it does what really quickly? It goes really fast. What do you see right here, folks?
what happens now? Anyone who has been to the beach knows the answer.
What would you call this? Like, give me a name that we talked about today.
Is that an eddy?
It's an eddy,
Yep.
which means now that we have an eddy which must have kinetic energy of the eddy. The kinetic energy of that eddy came from the mean flow that got transferred into it. But because it's an eddy, what must it be doing?
Mixing?
Well, it is mixing, but what did we say earlier in class that an eddy does?
Tries to get the atmosphere back to stability.
No.
From potential to kinetic?
Yeah, but what does an eddy do? We highlight it in the book.
Transfer of energy?
An eddy dissipates kinetic energy. We talk about eddies in the boundary layer. We talk about clear air turbulence. Anytime you have a turbulent eddy, you are dissipating kinetic energy. That is will lead to eddy viscosity. So kinetic energy must be being alleviated through an eddy.
Topples over. Note that the toppled wave moved out of our picture, which means the leading edge of the wave is traveling faster than it was before it toppled.
Now, in this case, if it's dissipating kinetic energy, where does it put the kinetic energy? Where's the kinetic energy going to do?
The potential?
No, it's not lifting the center of mass in any way.
Is it going to turn into internal then?
It's an internal energy is temperature, right? It's going to get warmer. So you have the potential goes to kinetic. Kinetic gets converted into smaller scale kinetic. It gets dissipated. Dissipation of kinetic energy is increasing the thermal or the internal energy, which is a function only of temperature.
Let us watch the steepening again with the camera moving at the speed of the toppled wave. Note that the toppled wave continues in its turbulent condition and does not change its shape. It also travels at constant speed.
So you see, now they're going at the speed of this leading edge of this toppled wave, and you get this, it's coming up, it's going to be so cool. You get this really cool plume, and once it does that, then the speed remains constant until it crashes into a wall.
The speed of the toppled wave, which is called a positive surge wave in hydraulics, depends on both the depth ahead, H1, and the depth behind the wave, H2.
Now, you've seen surge waves, probably whenever you clean your dishes.
Here you see 3 channels with water 4 inches deep in them. We are going to send positive surge waves down these channels with depths behind the waves of 6 inches, 8 inches, and 10 inches. The larger the depth behind the wave, the faster the wave travels. In fact, it can be shown that large amplitude wave speed, that is the speed of a positive surge wave, depends upon the depth ahead and behind as follows. Square root of G times the average depth times the ratio of the depths.
It can be shown, so they're not showing it in this video.
Small amplitude waves ahead of the surge wave move at the speed square root of GH1 relative to the fluid. If you compare these expressions, you will see that this local wave speed is always less than the speed of the surge wave. Thus, the surge wave catches up to small amplitude waves ahead of it. Small amplitude waves behind the surge move relative to the fluid at a speed square root of GH2. However, behind the surge wave, the fluid is moving. There is a drift speed of the fluid, U. And the drift speed plus the local wave speed is always greater than the speed of the surge wave.
That'd be a fun thing to prove,
Thus,
wouldn't it?
small amplitude waves behind the surge wave and moving in the same direction as the surge wave always up to it. In reality, these surge waves move at a fair clip.
Why did they don't redo this video is beyond me.
There is zero velocity ahead of it and a drift velocity behind it. By moving the camera, we have superimposed on the motion a velocity equal and opposite to the speed of the surge wave. In this reference frame, the fluid ahead appears to be moving into the wave front. The wave appears stationary, and the fluid behind has a net velocity in the opposite direction to the drift speed. We say the flow is steady in this reference frame. We can produce exactly this situation in a flume. This is a stationary wave called a hydraulic jump. The structure of this turbulent wave is very complicated and difficult to analyze. However, if we consider the fluxes of mass and momentum into and out of a control surface like this, we can determine the velocity and depth behind the hydraulic jump, given the velocity and depth ahead of it. The ratio of entering fluid speed to the local wave speed is called the Froude number. The Froude number ahead of the jump, F1, is always greater than unity. That is, the fluid speed ahead is greater than the local wave speed. We say the flow ahead is supercritical, or shooting. The Froude number behind the jump, F2, is always less than unity. That is, the fluid speed behind is subcritical, or tranquil. We can easily show this in the flume. A disturbance behind the jump catches up with the jump. A disturbance ahead of the jump is washed downstream into the jump.
Froude numbers,
This is only
F-R-O-U-D-E.
describing the steepening effect we talked about earlier.
You will use that in, sometimes when we get cold air damming,
Small
they'll deal with the
amplitude
Froude
waves
number.
behind a positive surge wave catch up to it.
Froude.
Small amplitude waves ahead are overtaken. Energy is being dissipated in the turbulence and foaming in this jump. The pitot tube measures the total head, the sum of the potential and kinetic energy. Notice how the total head drops as we move.
So what you're seeing is a tube of water that gets pushed
mechanical
up.
energy is being converted into internal energy.
There you go. So that the water that you push up is much higher ahead of it than over here.
Is dissipating about 1/3 of a horsepower. Below big dams, hydraulic jumps and stilling basins may dissipate thousands, even millions of horsepower. The temperature rise is hardly noticeable, however, since a total head loss of 778 feet is required to heat water 1 degree Fahrenheit.
Okay, so think about this for a second. I mean, if it's a little bit over exposed on this video, I don't know why it's poorly done, but the fluid comes in there and you get this hydraulic jump and you're dissipating kinetic energy. And they're using it in terms of horsepower, we would say joules. Huge amounts of joules. But the water temperature doesn't go up very much. Why? Because water has such a high heat capacity. Right, the specific heat of water is so high. You can throw lots of joules into water and you're not going to do that. But do you agree that in air you can get a much more significant jump because it's a much smaller specific heat?
You can see hydraulic jumps all around you if you are observant. Have you ever seen this one in your kitchen sink? The water spreads out at a supercritical speed from under the tap
So here's the water coming down and it creates this. I mean, this is, again, overexposed, so go do it at home. Put water on there and you'll see the hydraulic jump on your plate. So you could say, okay, the water speed is supercritical, then it goes to subcritical, as the Froude number is greater than 1, and here it's less than 1, and then you're dissipating kinetic energy over this flume, I guess they call it flume. And that is what's going on with your plate. So you've got much faster water overtaking much slower water as it drips off your plate. So if you're ever cleaning your dishes and you want to impress somebody, just say, oh, look at the water, supercritical speed before it jumps into the hydraulic jump and then becomes subcritical. Good. I wonder what the Froude number is. And the Froude number is based upon the depth of the water on both sides of this. Then you'd be an ultimate geek. And then people will say, well, isn't weather just about guessing what the weather is going to be? It's not like it's rocket science. And you go, well, yes, it is.
Goes through a cylindrical hydraulic jump, moves at subcritical speed to the edge of the dish, and spills over the edge. Although gravity waves in liquids are easily seen, they're not the most common waves we encounter in fluids. Compressibility waves in gases are certainly more common, since sound waves are compressibility waves. Sound waves are small amplitude compressibility waves. A large amplitude compressibility wave is a shock wave. Compressibility waves move at very high speeds and can usually be seen only with the aid of special optical devices. On rare occasions, if the light is just right, shock waves may be seen with the unaided eye.
So there's a rocket or there's a jet.
However, we can easily detect the passage of a compressibility wave by the changes in pressure associated with it. Our ears, for instance, are very sensitive detectors of pressure changes. Indeed, we classify all small amplitude compressibility waves, whether they're audible or not, as sound waves. As a model for a gas, here you see many particles floating on the surface of water, more or less evenly spaced. The number of particles per unit of surface area represents the density. As a compression wave comes along, you can see the particles accelerate in the direction of the wave motion. And you see the density increasing, that is, the particles moving closer together. Much of what we have shown you concerning one-dimensional gravity waves applies equally well to compressibility waves if we simply replace the depth of the fluid h by the density of the fluid rho. In fact, a compressibility wave may be described as a region of increased or decreased density that moves relative to the fluid. Just as depth is proportional to the amount of fluid per unit length in an open channel, so density is proportional to the amount of fluid per unit length in a closed channel. The fluid flowing into this length of open channel increases the depth. The fluid flowing into a length of closed channel increases the density. In a compressibility wave, the pressure depends on the density. Just as in a gravity wave, it depends on the depth. Although surface gravity waves and compressibility waves behave quite similarly, they are propagated by entirely different physical mechanisms. The fluid acceleration in gas waves is due to elastic forces associated with the compressibility of the fluid, rather than gravitational forces. The speed of a small amplitude isentropic compressibility wave increases with density, just as the local wave speed of a surface gravity.
Notice they use isentropic, so they're saying it's not being heated. You're not adding any heat to this, but you're going to get temperature changes because as it compresses, temperatures change. So we don't want to use the word isothermal, we want to use the word isentropic.
Wave increases with depth. This increase of sound speed causes compression waves to steepen.
I'm sorry,
When we
this is
say
bad
that the
video.
compression wave steepens, we mean that the density and velocity gradients increase in the wave. What happens when these gradients become very high? That is, when the wave becomes very thin. The compressibility wave cannot topple over like the surface gravity wave. Instead, the density and velocity gradients reach limiting high values in a thin region and remain constant.
Okay, limiting high values. So notice remember the water is going really fast and then it goes to the plume. And there's the dissipation of energy. And we just made it really very, 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 very small, very thin, high gradients. Okay, what was the number? The number that we used to say, what did we say the number was greater than 1 here and less than 1 here?
Freudian numbers?
The what number?
Freudian?
Freud, F-R-O-U-D-E. So Freud, I don't know how to pronounce it exactly, Freud. For this, anybody know what that's going to be? It's going to be called the Mach number, M-A-C-H.
By looking from above at only the inflow and outflow of an hydraulic jump, we can gain an impression of the steep velocity gradient. In compressibility waves, these limiting high gradients are determined by the effects of viscosity and heat conduction, which up to this point we have been able to ignore.
Because water has high heat capacity.
The reason the viscous forces become significant here is that fluid particles going through a steep wave experience high rates of deformation. Viscous forces are proportional to the rate of strain. Hence, viscous forces become significant in a steep compression wave.
Too bad you don't see
The
that.
steepening tendency is opposed by the action of viscosity and heat conduction, and a limiting steep wave results, called a shock wave. Stationary shock waves can be produced in a supersonic wind tunnel. Here the gas is moving at supersonic speed ahead of the shock, Mach number greater than 1, and at subsonic speed behind the shock, Mach number less than 1. This is analogous to the stationary hydraulic jump we saw in the flume, with fluid moving at supercritical speed ahead of the jump and subcritical speed behind it. Recall that the total pressure, total head, dropped in going through a hydraulic jump. In the same way, total pressure drops in going through a shock wave because some of the mechanical energy is changed into internal energy by the dissipative action of viscosity and heat conduction.
There you go.
Unlike the hydraulic jump, a shock wave is extremely thin, on the order of a few mean-free paths thick, about 1/millionth of an inch at room temperature and pressure. A moving shock wave is what you hear when there is an explosion. The thunder that accompanies lightning. It is the sonic boom you hear from the supersonic airplane. We can produce moving shock waves in the laboratory in a shock tube like this one. We put high pressure gas on one side of a frangible diaphragm and low pressure gas on the other side. The diaphragm is made of cellulosic sheet. We break it with a knife like this. So with high pressure gas on this side and low pressure gas on this side, when we break the diaphragm, we create a shock wave which moves at supersonic speed down the tube. By pulling a gate in the wave channel, we can produce a positive surge wave.
Cool people.
This is analogous to the shock wave in this tube. This end is open, and we have placed streamers here to make the motion of the air visible. Now I will break the diaphragm. You notice the wind behind the shock wave, just like the drift speed behind a positive surge wave. An atomic blast sends out a spherical shock wave, followed by a strong wind, which is the air moving at the drift speed.
There's better video quality.
It
At
produces very strong
least the
shock
sound
waves
sync.
in this shock tube. The high pressure section is here. The low pressure section is this Pyrex tube. The temperature behind a very strong shock wave can become so high that the gas molecules are torn apart, dissociation, and even electrons stripped off the atoms, ionization. Ionized gases emit light, and hence this phenomenon is easily seen. The diaphragm is located here. This is what a diaphragm looks like before it is broken, and this is what it looks like after it is broken.
There's a
You
metal
can see that
disc.
we're dealing with very strong pressure forces. We have argon in the low pressure section of the tube. You will see the shock as the argon ionizes. I'm going to turn down the lights. You watch the tube. Now I will break the diaphragm. So far, we have concentrated on one-dimensional waves.
So that's kind of cool though, right? You get the idea is that you have such incredible amount of pressure gradients that there's such an acceleration, you're stripping electrons off of gases. That's
Two
really
and
cool.
three-dimensional waves involve the same basic concepts, but can become very much more complicated. These remarkable pictures were taken at nearly 400,000 frames per second. This sequence shows a normal shock wave passing over a wedge. Here, a shock wave passes over the sharp edge of a flat plate. Notice the vortices produced at the sharp edges.
Okay, so over here you get this vortex over there, which is, again, vorticity comes from shear. The speed of the winds are changing. When they're designing airplanes, they have to be careful of this. This is why airplanes don't usually go faster than about 0.8 Mach. Because even at 0.8 Mach, when you've got parts of the airplane wing, you actually create shears that create supersonic flow, and that supersonic flow can create a sonic boom, and that would be bad. So you've got to design an airplane so that even the little parts don't go above the speed of sound. Because if they do that, then you start to get explosions and sonic booms and break windows and all that other stuff.
And the great number and variety of shock reflections and interactions. We have shown you some wave phenomena in fluids, chosen to emphasize the basic concepts of wave propagation. First, the local accumulation of mass, which is due to depth changes.
Well, and then that's just a summary. And that's waves and fluids. Again, why we can't do this, I don't know about you, but that just, it shows me so much to think about when I watch this. And then I understand these equations so much better. It seems like lately we throw equations and like, here's what's going on. You're like, what are you talking about? Have you ever dealt with further numbers, Allison, in dynamics yet? Okay.
No.
You might, but this is all kind of senior level stuff. So, but I thought we should end the class with that. You talk about viscosity, just understanding the basic principles over and over. As you go forward, you will start to go, okay, I can put any of these things together. Just remember the basics. So that's intermediate. I was pretty pleased with the quality of what we did in this course. I think we did everything that we needed to do. I thought we get a really good background. It wasn't until Brent a couple of years ago when we started realizing that the dynamics that we do in the second part of the class helps people a ton in their dynamics courses. which I didn't know that I was doing for people. So there's intermediate. I wish we could continue on and do mesoscale together. That would be fun. Maybe we should next year. And I like the record. I like this section.
What are you teaching next semester?
Oh, just the basic intros, nothing major.
You're not
Or
doing
that-
meso? You're not doing meso?
No, I won't do. Maybe I don't know if I'll ever do meso again. It might be up to Ron at this point. So we got 2 Nicks in our class. There's another Nick, and
For
he's,
severe.
yeah, he's gonna,
Alberts, I believe.
yeah, he's going to be
Yeah.
another one that's going to do 2.5 plus 1.5. So we'll
Yeah.
take care of that once we're back in school next fall, and we'll
Okay.
get that agreement signed and everything.
Yep, he's in my forecasting class with Ron. So
Yeah, that's cool. Yeah, he's good in my intro class, so we've got him to do intermediate, but we'll see. Any
All right.
questions, comments?
the lectures that you forecasted, it looks like you all post them under like somewhere in the COD weather website. Are those always going to be there that we can go back and watch if we want to?
Yeah, I'm going to keep the lectures for intermediate there all the time. I'll probably get rid of the other ones because they're my classes, but the intermediate ones is kind of an interesting, that's something I want to keep up there. And I think for next semester, the 11-15, because I'm going to do some of it virtual and some of it just lectures. So I'm going to, here, if you go to climate.cod, you know where our stuff is, go to 11-15.
Yeah.
There's, those are lectures I'll get rid of, but there's going to be topics. So I give non-student, they're not participating lectures.
Okay.
And that's what's going to happen. So those will be there. So you can always look at anything we've got in there, and I'll try to have some more names to it. Okay, guys. Hope you have a great Christmas. Good to see you. Congratulations, Allison. I think that's really awesome.
Thank you. When I was talking to my dad, the garage door broke. So I was trying to figure out what we were going to do with the garage door.
Oh, well, you can always release it and use it manually.
Yeah, that's what he was doing. He had to move my car.
Yeah, it's heavy. Okay, guys. Merry Christmas.
Merry Christmas.
And
Merry
we'll
Christmas.
see you. I hope you guys can take other courses. Take forecasting.